Assalamualaikum warahmatullahi wabarakatuh, students of Tamhidi Science. Lesson 58 is reactions of organic compounds. The things that we need to learn is the difference between homolytic and heterolytic cleavage, together with reaction intermediates, carbocation, carbanion free radicals and their stability. What are electrophile, nucleophile, and the main types of organic reactions: addition, substitution, elimination, and rearrangement. In any reactions, we usually write the equation starting material or reactant becomes the product. For organic reaction, we need to add two more categories. Number one is reagent. Reagent is the chemical substance with which an organic compound reacts. So a substance from the reagent will enter the organic compound, will interact with the organic compound and becomes the product. The difference with condition is that condition is a situation or something that will boost or initiate the reaction. For example, temperature, solvent, light or energy, heat, catalyst, and the environment, whether it's acidic or basic. There are two different ways on how to write the equations. First, this is the reactant, this is the reagent, and this is the condition. The condition is put on top of the arrow, whereas the reagent is put after the plus sign. The reactant and the product is in normal place. The second way is that we put the reagent on top of the arrow and the condition at the bottom of the arrow. Okay, this would definitely save space, of course. There are different types of arrow in organic equations. The first three we have done previously. The first here is the reaction arrow drawn between reactants and products. This is a normal one. And then the second one is the equation arrow, where we know that we can use this for a reaction that goes forward and reverse at the same time. And then the third one is an arrow that we use for resonance structures. We've learned this in Chapter 5 last semester. This is called double-headed arrow. Okay. The fourth one is called full-headed curve arrow. This arrow can go anywhere and it will curve to the right, it will curve to the left, it can curve to the part where an electron pair will move. Okay? There is one more arrow. This is an arrow which have only half-headed. We also call this arrow as fish hook arrow. It shows the movement of one electron only. Next, we are going to look at types of covalent bond cleavage or fission. Cleavage means the break of bond, and when we are doing reactions, it will involve breaking and making of bonds. There are two types of breaking, which is homolytic cleavage and heterolytic cleavage. Let's look at the first one, homolytic cleavage. Homolytic cleavage is a breakage that occurs in a non-polar bond. It involves two atoms of similar electronegativity. A single bond here, a covalent bond, breaks symmetrically into two equal parts, and one atom will take one electron each, forming free radicals, and it usually happens in non-polar organic compound, for example, alkane. Basically, when we are learning chapter 5, hydrocarbon, free radical substitution would happen on alkane, and homolytic cleavage is one of the things that happens in the reagent of the substitution reaction. This break of bonds need high energy, and usually we use UV light from the sun. And if there's no sun, we want to do the reaction at night, we can use high temperature as high as 200 degrees Celsius. Example given here is when you have a diatomic molecule where you have a covalent bond in the middle between a similar atom because it has similar electronegativity. You can see the arrow is a fish hook. There are two fish hooks over here. So one electron will move to the left atom and another electron will move together to the right atom, meaning that UV light is powerful enough to break this bond between the two stable atoms. Hence, we're going to get two similar free radicals. We call this reaction intermediate as free radical. The second cleavage is heterolytic. If homolytic happens in non-polar bond, heterolytic, on the other hand, would occur in a polar compound involving unsymmetrically compound. Compounds would be separated into unequal parts. One part is an ion, for example, and another part would be a carbocation because they have different electronegativities. The covalent bonding would break, and then the bonding electron will be transferred to the more electronegative part. For example, HCl, Cl would take both of the electrons and becomes an ion, and then another part would be H. H is cation, but if we involve a bigger part of organic compound, it would become carbocation. Okay, this happens in polar organic compound, for example, methanol, haloalkanes such as chloropropane, for example. So we need high energy to break this kind of bond. So let's look at an example where we can put the different parts of the compound into an unknown A and B. In the first situation, we look at A is being more electronegative. So A would become the anion, taking both of the electrons with it, and left B as a cation, B+. But what if we reverse the situation and make B the more electronegative atom? B would take both of the electrons and become the anion, and then A+ is left with no electrons at all. It became the cation. Reaction intermediates are a derivative of initial material formed before the desired product is produced in a chemical process. So we have three types: carbocation, carbanion, and free radical. These three are unstable and highly reactive. Let's look at the first one, carbocation, which can also be called carbonium ion. It is reactive with a positive charge at carbon, and it is formed in heterolytic cleavage. Let's look at example 4.10. As you can see here, this carbon is a tertiary carbon because it is attached to 1, 2, and 3 methyl group. So it is attached to a Cl. Cl here is more electronegative than the rest of the compound, making Cl taking away both of the bonding electrons to itself. So Cl minus becomes the anion, and the rest of the compound becomes a carbocation or carbonium ion, and you can see here the positive charge is at carbon. The CCl bond breaks heterolytically, and both bonding electrons are transferred to chlorine atom, forming anion and carbocation. Carbanion is an anion which is a trivalent, meaning that it has 3 bonds, and it carries and it bears formally a negative charge because it takes both of the bonding electrons toward itself. It's also formed from a heterolytic cleavage. For example, 4.11, we can see here lithium is more electropositive than the carbon. Therefore, this carbon, which is the tertiary carbon here, it will take both of the electrons from this covalent bond to itself, and it will become carbanion, and left lithium as a cation. Free radical is a species that has an unpaired electron, and it will always take electron from other species or other molecule so that the electron that it has is paired. In biology, free radicals are dangerous because it robbed or it took away forcibly the electrons from other cells. So it will spread a lot of disease. And this particularly free radical formed from a homolytic cleavage. So let's look at example on how do we produce free radical. It needs a lot of energy from UV light here. UV light are from the sunlight, or we can use a high temperature as much as 200, 400 degrees Celsius. So what happened is, this is a single covalent bond which has 2 electrons, and 1 electron will go to the left chlorine molecule atom, and another one of the electron will go to the right chlorine, and it will form 2 free radicals like this. So this free radical will continue on doing its reaction towards the other compound in the solution. If we put in propane, it will propagate propane to become chloropropane because this free radical Cl dot now is trying to take away the electrons from the other compound. So this is what we call free radical substitution. We will learn more in chapter 5, hydrocarbon, the reactions of alkane. So when we are doing a reaction, a chemical reaction in organics, we would be faced with a situation whereby we don't know which product we are going to produce, whether it is primary, secondary, or tertiary, haloalkane or alcohol, and so on. So we need to know about their relative stabilities. If in the compound we have carbocations, we need to know which one is more stable in order for it to become which product. So we need to know their stabilities, and therefore we need to know their classifications. Carbocation, carbanion, and free radical can be classified into primary, secondary, and tertiary. So let's first look at carbocation. A methyl cation is a carbon which has 3 hydrogens around it having a positive charge. So that is methyl cation. For primary carbocation, it has 1 R attached to the positive carbon, and so on, secondary and tertiary as we go along. Those are the categories for carbocation. So the more alkyl group that is attached to the positively charged carbon, the more stable the carbocation is, because it would have a greater dispersion of the charge, and therefore the stability of carbocation increases with the number of alkyl groups present. So now let's arrange the class of carbocation that I mentioned just now. Firstly, the least stable would be methyl cation because it has no alkyl group attached to it. It only has hydrogen atoms. And then primary carbocation has 1 methyl group or ethyl group attached to it. It is more stable than methyl cation. And then we have secondary, and the most stable would be tertiary. This is the arrangement or the rank of increasing carbocation stability. It is more stable for tertiary carbocation. Now, the difference with carbanion stability is that carbanion depends on the S character. S character is a contribution of S orbital towards the hybridization of the charge-bearing carbon, meaning carbon has negative charge, and then if it has hydrogen attached to it, because hydrogen has S orbital, the S character is higher, so it would be more stable. Therefore, if you have alkyl group it will destabilize carbanion because alkyl group is CH3, CH2, CH3. It's not having any s orbital. Therefore, we can see here electron withdrawing group. We're going to learn about this EWG in chapter 6, arene. If we have EWG, for example, halogen, it will destabilize carbanion because it's going to have an inductive effect on the electron density. This is another factor that will affect the stability of carbanion. So let's look at the arrangement of the stability of carbanion. It's the other way around from the carbocation, whereby here we can see methyl anion having a lot of S character, a lot of H atoms around the negatively charged carbon, making it the most stable and more active. And then we can see the least stable would be here, the tertiary carbanion. The increasing stability is to the left there. Okay, you can see tertiary carbanion is less active than methyl anion. The stability of free radicals is the same as carbocation in the sense that they are electron deficient. So as we have more alkyl groups attached to the carbon with unpaired electron, it would become more stable. So what we would have here is that the tertiary free radical on the far right is the most stable free radical compared to secondary, primary, and methyl radical. Let's look at these four compounds. Which one is the most stable free radical? The first compound here, let's redraw so that we can see whether it is a primary or a secondary or a tertiary or a methyl. This is one R here, so this one is primary. And what about the second one? Let's draw, okay, the radical is on the right, so this is that carbon, and then the H on the right I draw on top, and then in the bracket there I put one methyl here and another methyl here. So this is 1 and 2R. Therefore, the second compound is secondary free radical. The third one is basically a methyl radical. It has no alkyl group. But the fourth one is something different. Okay, let's draw the carbon, which has the unpaired electron over here. And then this is the carbon next to it. And then it has a carbon here. Remember, the skeletal structure is for every point or every side. There would be one carbon. So here is one carbon, 2, 3, 4, 5, 6. So this is a cyclohexane. And where is the alkyl group? The alkyl group is basically here. We actually have H over here because we want to complete the number of carbon bonds as 4 bonds from each other. So here is an alkyl part, and here is an alkyl part, whereby we can categorize this free radical as secondary free radical. So what would happen is we have two free radicals, which is more stable, which is compound number 2 and also compound number 4. That is the answer for this exercise. In organic reactions, we have reagents and sites. Electrophile or electrophilic site is a species or a place where it is lack of electron, and it would be accepting electron from an attacking nucleophile. Electrophile is electron loving and it can be either neutral or positively charged. As listed here, we can see the examples of electrophiles are cations such as hydrogen ion, hydronium ion, nitrite ion, and carbocations. Lewis acids, as we have learned in Chapter 7, Sem 1 last semester, aluminium trichloride, ferrum trichloride, and boron trifluoride. These are the trigonal planar molecules that will receive electron when donated from other species. You have to remember the definition of Lewis acid. And then we have oxidizing agents such as chlorine and bromine gas. When we have a site where the electron density is low around a polar bond, such as carbonyl, haloalkanes, and hydroxy compounds, we call this place or this site as electrophilic sites. These sites are electron deficient and is available to receive electron from nucleophile. If the electron is from nucleophile, it will attack the electrophilic site. Electrophilic site will receive the electrons given by nucleophile. But if we have an electrophile, it will receive electron from nucleophilic site. Okay, so that is basically how it goes in the mechanism of an organic reaction. I've been talking about nucleophile. What are they? A nucleus loving, meaning that it has a lot of electron. It is electron-rich species and it will always donate electron. It can be either neutral or negatively charged. Anions such as hydroxide ion, alkoxide ion, chlorine ion, cyanide ion, and carbanions are examples of nucleophiles. They have a negative charge on the carbon atoms for carbanion. Lewis bases also is an example of nucleophile. What is Lewis bases? The species which donate lone pairs of electron. Ammonia, water, and hydrogen sulfide. All these three has electron lone pair. So when looking at Lewis bases, you should be imagining the trigonal bipyramidal band shape of these structures, because having a lone pair, it will repulse and make the shape unsymmetrical. Chapter 5 is coming back in a flash to you as of this instant. If we have nucleophile, we also have nucleophilic sites where we have a lot of electrons there. The density of electron would be high at the carbon-carbon unsaturated bonds, such as double bond and triple bond in alkenes and alkynes. Benzene ring also is a nucleophilic site. Okay, the last part of this lesson is types of organic reaction. There are 4: addition, substitution, elimination, and rearrangement. Addition is when you add atoms or groups to a multiple bond, meaning that we need to have a nucleophilic site, an alkene or a carbonyl. So the 2 types of addition would be electrophilic addition and nucleophilic addition. In electrophilic addition, an electrophile, bromine, for this example, will attack a nucleophilic site of an alkene, this is a propene, and it will take the electrons from the double bond and form a dibromopropane here. This is a typical reaction of unsaturated compounds such as alkenes and alkynes. But in nucleophilic addition, this reaction is initiated by a nucleophile. Nucleophile will attack an electrophilic site. This is a reaction of a carbonyl compound. What are carbonyl compounds? A ketone or an aldehyde. As you can see here in example 4.14, the reactant is a type of ketone. The carbonyl group is in the middle. It has 1, 2, 3 carbons. So this is a propanone. The nucleophile which will initiate the reaction would be the cyanide ion. It will attack the electrophilic site here, and it will form this compound where you have a CN cyanide group and a hydroxy group. Substitution reaction is a reaction in which an atom or group in a molecule is replaced by another atom or group. There are 3 types: free radical, electrophilic, and nucleophilic. We have seen this reaction, free radical substitution, when learning about homolytic cleavage and free radical formation. This is Cl2, the one that will initiate free radical substitution, undergoing a reaction to produce free radical Cl dot. Substitution here involves free radical as intermediate species, so we need UV light or sunlight to make this reaction. This is a reaction on alkane. This is an ethane. It will form chloroethane as a product. Electrophilic substitution, on the other hand, is involving aromatic compound, i.e. benzene ring. The aromatic nucleus has high electron density. Thus, it's nucleophilic and prone to electrophilic attack. Example 4.16 is showing to you how benzene ring reacts with Br2, an electrophile, by the reagent and conditioned ferrum, producing bromobenzene. Nucleophilic substitution is a reaction of saturated organic compound bearing polar bond, such as haloalkane and alcohol. They will replace halogen with hydroxy or hydroxy with halogen, vice versa. However it is, bromine and hydroxy group will replace each other in this carbocation. The third type of reaction is elimination. We eliminate certain atom or group from a carbon atom of a molecule in order to form unsaturated covalent bond. This is a reaction where we are going to produce an alkene. This is an ethene. It has a double bond. So how are we going to form ethene? By removing or eliminating one hydroxy group and one hydrogen atom from an ethanol. Rearrangement reactions are more complicated. This is a reaction where atoms or groups change position, and it occurs in a single reactant perhaps, and it will reorganize the bonds and atoms. Tautomerism is an example of a rearrangement reaction. Let's do practice 4.8 together. You have more questions in the tutorial section. Please do it all. Number 1, this is a propene and we want to insert Br in the middle of the compound and at the end. So this is basically electrophilic addition. Second, this is an aldehyde. Aldehyde is now becoming an alcohol. So what happened here is a nucleophilic addition. Number 3, this is a benzene ring, so we know immediately this is electrophilic substitution. Number 4, we have a UV light. Of course, this is a free radical substitution. And finally, number 5, we have a haloalkane over here and we form a double bond. So this is an elimination reaction. Voila! Yes, this is a long lesson, but it's essential for you to start organic reaction. Thank you very much for paying attention to me, and I hope you would go for second and third gear now that we learn how to name the compound and how to create the equations already. We have look at the species that involve, types of reactions, types of reaction intermediates, and so on. It should be a smooth ride after this. So, bye everybody. See you again next time. Assalamualaikum warahmatullahi wabarakatuh.